Hello everyone and welcome to lecture today. Today's lecture, I just wanted to summarize the number of different applications of the triple integral. And overall, the applications that we're going to focus on are going to be very similar to the applications of the double integral in 2D. But this is now for regions in 3D, so three-dimensional regions with a distributed mass. And the main things that we're going to talk about are going to be the applications of the total mass, so calculating, and I'll write down that this will be the applications. Of the triple integral. And specifically, we'll be talking about the calculating total mass or total charge, so total electric charge, given a density function and on this exact same note, we can also generalize the center of mass or the center of charge which in a very real sense give us a sort of average location for the center of the mass density function or the charge density function. We can also get, using the center of mass idea, very similar to before, the centroid of any shape in 3D, which we'll recall the centroid is the geometric center of an object or a domain in 3D. And lastly, we'll talk about the moment of inertia. About a line L, and specifically talk about the moment of inertia about three specific axes: the x-axis, the y-axis, and the z-axis. So in order to calculate total mass, and I'm not going to go over the derivation of the following formulas. These derivations of these formulas are very similar to the two-dimensional case. The main difference is that we're now dealing with, say, a distributed mass or distributed charge density within a three-dimensional region. So we assume we have some coordinate system here, x, y, and z, and assume that we have some three-dimensional region. This region could be a beam, so a construction column. It could be say some sort of piece of an electromagnetic device that you're building, so like a circuit board or some other piece that you're interested in the electromagnetic properties of, like the charge of a capacitor on a circuit board maybe, or some other device. We'll call this region omega, And just like in the other lecture on the triple integral, we'll assume that we have some density function, and throughout we'll deal with a mass density function. So there's some regions in this object where the mass is very, very heavily concentrated. That's, see, this red region right here, okay, this red region right here, and then this region right here. You see we have a very heavy concentration of mass at these locations, and then maybe if you move a little bit away from these regions, you have a slightly less of a concentration of mass. It's still relatively dense, but maybe a little bit less dense than around these red centers, or these red concentration areas. And then assume as you move far enough away, the density is very small relative to the density in the red area. You have much less density than in that red area, or even the green area. So the mass density is very, very low in these blue regions that I'm kind of drawing here. And this is the general scenario when you're dealing with general materials. General material in 3D does not have a constant mass density function. It's changing over the entire material. A great example of that used directly in engineering applications is composite materials. So we assume that we have some function. It's a function of three variables, rho of x, y, z, and this function is the mass density function, or the mass density at the point x, y, z. So using Riemann sums, just like before in our definition of the triple integral, we can directly go through and show very, very clearly that the total mass contained in the object omega is going to be exactly the triple integral of this mass density function over the domain omega. This is coming directly, justification of this comes directly from the Riemann sums. And this is important to remember. This is what's called rho here. It's a volumetric mass density. So it has units of kilograms per meters cubed, say. That's an example set of units. You can use any units for mass or length that are relevant to the application, but the typical units are, of mass are kilograms and meters. So the units of the density function is going to have units of mass over volume, and that will make the units of this procedure work out really nicely, in that this integral is the integral of a function that has units of kilograms per meters cubed. You're integrating with respect to volume, which also has meters cubed. So the final units of this expression will be in kilograms, which is the units of mass. So this is the first main formula that we have that gives us, a means of applying the triple integral and actually calculating, actual mass of a given region. In much the same way, and I'm not going to draw a picture. You can just kind of think of, instead of having a mass density function, you might have charge density function. We call that a lot of times sigma of x, y, z. At the point x, y, z. And sigma here could, for instance, maybe have units of coulombs per meter cubed. It's like a volumetric charge density. This is a very typical thing to have in applications. And then to find the total charge contained in a region, you would take the triple integral of that charge density function. over the region omega. So the idea here is that this is a very useful idea. It's basically saying that really, if you have a density function, regardless of what that density is representing physically, the triple integral of that density function over a three-dimensional region will give you the total amount of that quantity in your region, which is a very, very useful idea. So this is, the justification of this, like I said before, is directly from Riemann sums in 3D, in the definition of the triple integral that we talked about earlier. In much the same way as the total mass and total charge were calculated using for the double integral in 2D. So this is the first big application. Along these lines, we can talk about the center of mass, or the center of charge, if we're doing a charge density function. And again, I'm not going to rederive these formulas in 3D, because we already went over the derivation via Riemann sums in 2D, but the formulas are all very, very similar. So the center of mass, the x-coordinate of the center of mass, given a density function, is going to be the moment, it's called the first moment, about the yz plane over the total mass. We have the formula for the total mass before, using the triple integral. So just like you would expect from the previous application in 2D, this moment myz, when you derive this formula, ends up being exactly the triple integral of the density function times x. And similarly, the y coordinate of the center of mass is going to be the moment about the xz plane divided by m, or the first moment, this is the first moment with respect to the y-axis. And this is very, very similar. It's going to be the triple integral of the density function times y. And lastly, the z-coordinate of the center of mass is going to be the first moment for the z-axis divided by the total mass, which is evaluated very, very similar to the other two integrals. The other two moments, this will be the triple integral of the density function times z dv. So there you have it. In order to calculate the center of mass for a region, you have to calculate the total mass, which is a triple integral, and then you have to calculate these three moment integrals and use the center of mass formulas for any region omega and any density function rho. These formulas are very, very similar to the formulas for double integrations in the center of mass in 2D. The only difference is that now we have to take the triple integral over a three-dimensional region, and we have a function in general that might be of three variables, x, y, and z. It's important to also note that we can use very, very similar formulas, almost the exact same formulas as the ones we've defined here, to define the center of charge. which is in some sense like an average center of the charge density function or charge distribution on some charged object. The only difference here would be that you take these direct formulas and instead of using the mass density, you would use the charge density function. So replace all of those rho functions with the sigma functions, the actual charge density of the region that you're interested in. And I think I have enough space on this page. I'll also include the centroid on this page. We can define the centroid of any three-dimensional object, or the geometric center of the object, by taking the above equations and setting the mass density equal to constant. So if you do that, the constant will actually end up canceling out and will give you that the coordinates of the centroid, just like in 2D, are the average value of every coordinate. Or you'll remember the formula from the average for the average value from the triple integral introductory lecture on properties. The average value of x will be the triple integral of x over omega divided by the total volume of the region omega, which is the triple integral of 1, the y coordinate of the centroid will be the average value of the y coordinate, which is the triple integral of y, the accumulation of the y coordinate divided by the size of the region, which is the volume of omega, or the triple integral of 1 over omega, and the z coordinate of the centroid is going to be the average value of z, which is the triple integral of z over the region divided by the triple integral of 1, which is the volume of the region. So the idea is that to calculate the centroid, you can go through and calculate, you have to calculate the volume of a given region using the triple integral, and then you have to calculate the integral of each one of the coordinates, and then you plug them into their respective formulas. But these are the correct formulas that will give the geometric center of any region at all that you're considering, kind of does like a geometric average. Now in general, the centroid is much easier to compute because you don't have a mass density function that you have to deal with. You only have these integral of x, integral of y, integral of z. So the main problem here is figuring out the correct coordinate system to use for your integral, and that normally depends on the bounds of the region of integration. Right, so it depends on the symmetries of your domain omega. But it's important that you know that, and you also know that it's the centroid is always, I shouldn't say always, but I'd say usually different than the center of mass. For a given mass distribution, mass density function, the mass is being distributed in different places in your region, and doing the calculations for the center of mass will give you a different value for the center of mass than the centroid. This is very, very important in engineering applications, because if you're trying to, say, build, use columns that are composite columns, or build something with composite material, you have to really think about where the true center of mass of your object is if you want to build it correctly and make sure that it's balanced when you're building it. So this is one of the real reasons why the center of mass and the centroid are both very important things to calculate in general. Oftentimes you want to use both of these points to help you engineer your object to satisfy certain optimal conditions. So these are the main three formulas that we have for the centroid. And these are the main three formulas that we have for the center of mass or center of charge of a given region. So if you want to calculate this point in general for a given region, you typically have 4 integrals that you have to go through and compute to calculate any one of these values. So the center of mass of the centroid. So all of those formulas as well, they come directly from the Riemann sum derivation of the triple integral that we talked about earlier. But I'm not going to go over that in this lecture, because I think the important thing in this lecture is just to get down the correct equations and how to use these equations to actually go through and compute the values of these quantities. So the last application that we'll talk about is what's called the moment of inertia of a given region. And we'll start by reviewing that we can actually do this, find that what's called the moment of inertia about any line. So let's say we have our region omega here. And assume that for some reason we have some reason that we're going to be, say, wanting to rotate this region omega around some line. We'll call it L. Where at any point on the surface, we'll call the distance between that point on the surface and the line r of x, y, z. And actually, instead of r, I think I'll use d, which just stands for distance from the surface. It's a function. At any given point, you have a different possible value of d of x, y, z. The distances for any given point in our region omega going to be different. So we can talk about the moment of inertia, and we can directly go through and define the moment of inertia, or the resistance, inertial resistance of the region omega to rotation around the line L. And this is directly, again, due to Riemann sums. You go through and can show from Riemann sums that this is going to be the triple integral over omega of the density function multiplied by the distance function to that line squared, which is essentially the exact same formula discussed and shown in 2D, only in 2D it was a double integral and all the functions were 2 variable functions. But in 3D it becomes a little bit more complicated because you have a 3-dimensional region. But the formula remains exactly the same, and the derivation is essentially exactly the same you're just going to be dealing with triple integrals instead of double integrals. Using this idea, we can go through and actually define specific moments of inertia about each axis. So the moment of inertia of this region about the x-axis is going to be the triple integral over omega of the density function times the distance of any point in this three-dimensional region omega to the x-axis squared, which will be y squared plus z squared. So this triple integral will give you the moment of inertia of any three-dimensional region about the x-axis, the moment of inertia about the y-axis will be the triple integral over omega of the density function times the square distance to the y-axis, which is x squared plus z squared. And lastly, the moment of inertia about the z-axis, so the resistance in motion to rotation, the resistance to rotation about the z-axis will be the triple integral over omega of the density function times the distance of any point to the z-axis, which is just going to be x squared plus y squared. And there you have it. This is how you go through and calculate the specific moments of inertia about any one of the axes. And this is another very, very useful tool for in mechanical engineering. It's also a useful tool in electrical engineering. If you, say, want to compute the moments of a charge distribution function, or the electric moments, you can also calculate those, and those give you a very interesting number that tells you, in some sense, a similar information to what the moments of inertia are telling you about the mass density function, which is very cool. So the main idea here is that we want to see a couple examples of applying these formulas, so we can go through and be okay with going through and using the formulas for a general problem to say stuff about a given region and a given applied problem that we're dealing with, say. So let's take for our first example the mass of a rectangular region. So we'll say it's like a beam. So we want to let's find all the properties. And I'm not going to go through and do all of the triple integrals, but I will do at least the first triple integral, and I'll set up most of the triple integrals so you can go through and verify for yourself what the correct values are. So let's find the mass, the center of mass, and the moments of inertia. Sometimes called the second moments. Of a rectangular region so this will be for x from 0 to 3, for y from 0 to 4, and for z from 0 to 3. This is kind of like you can think of it like a beam or a rectangular column. So there's a width of 3, a depth of 4, and a height of 3. With the density function, or a density function, of rho of xyz is equal to z times e to the x plus y. it'd be good to get a visualization of this in 3D. So that's why I have my custom Python code that allows me to make plots and visualizations of functions of 3 variables. You don't need this code, but the idea is that it does definitely help you visualize what's going on here. So let's open that up. I'll run the code right now, and then we'll open up the plot right here. And we see that this is a picture of this exact region, along with a visualization of what the density function is doing in this this shape. Now you see that at the origin, at 0, 0, 0, the density function is very small. It's close to 0. And then as you get larger and larger and larger, or as you get further and further and further away from the origin, the density function gets larger and larger and larger, which corresponds to colors moving from blue to red, to the point where at this upper corner right here, the density function is very, very high. And if we kind of move this around, you can see that this is definitely true. At that corner right here, or right around here, is where the maximum of the density function is. So the idea is that we want to figure out the mass of this object, the center of mass of this object, and the moments of inertia of this object. Because it's not going to be the centroid. The centroid of this object is actually relatively straightforward to calculate. If you go through and do the calculations for the centroid, I encourage you to do it. They'll end up reducing to just the very middle of this object, because you have a nice rectangle here. So the average geometric center will be the very center of this object. The center of mass will definitely not be the geometric centroid of the object, because there's more mass concentration up in the upper corner of this object. So to go through and calculate the center of mass, we have to go through and calculate first the mass, and then calculate the first moments, and then plug into the general formulas of each. So I'll go through exactly this first mass integral, but the other integrals I'm not going to go through. I'll set them up so you have the triple integrals there, but I'll encourage you to go through and do every one of the integrals yourself, to just kind of practice and practice your triple integration. So the total mass is going to be the triple integral over omega of the density function which is going to be the triple integral for x from 0 to 3, y from 0 to 4, and z from 0 to 3 of the function z times e to the x plus y. dz dy dx. E to the x plus y does not depend on z at all. So this is the integral from 0 to 3, from 0 to 4, e to the x plus y times the integral of z with respect to dz, or with respect to z. The antiderivative of z is going to be z squared over 2. So when we plug in here, you'll get 3 squared, which is 9 over 2. And you have the integral from 0 to 3. And the integral of e to the x plus y with respect to y, which is just going to be e to the x plus y, because the antiderivative of e is just itself. This is from 4 to 0, from 0 to 4. So when you plug in here, this will be 9 halves. The integral from 0 to 3, e to the x plus 4 minus e to the x plus 0, which is just e to the x. And so the last integral is this x integral of this function. which again is going to be itself because of e to the x plus 4 and e to the x both have antiderivatives that are identical to themselves. This is from 3 to 0. So when we plug in, we get that this is 9/2 e to the 3 plus 4, which is e to the 7, minus e to the 3, minus e to the 0 plus 4, which is e to the 4, minus e to the 0. Or 9/2 times 1 plus e to the 7 minus e to the 3 minus e to the 4. And this value is measured in, say, kilograms. If, say, the units of our density function is kilograms per meter cubed, then this value is the total mass measured in kilograms. So there you have it. This is how we directly go through and compute using this formula for the total mass. You just take your density function and you take the triple integral of it, and that will give you the total mass contained in your three-dimensional region. So this is the mass of that bar that we showed earlier. If you want to approximate, you can also approximate. So this approximately comes out to, when we go through and do that, around 4,600 kilograms. So this m, when you approximate, is approximately equal to 4,603.27 kilograms. For the center of mass of this region, we have to go through and use those center of mass formulas. You'll recall that for the x center of mass, the x center of mass is equal to the first moment of the x-axis divided by m. The y center of mass was the first moment of the y-axis, or the xz plane, divided by the total mass. And the z center of mass was the first moment of the z-axis, or the xy plane, divided by m. So we already have m, the total mass, and we have very nice triple integral formulas for each one of these expressions, all of the first moments. The first moment for x, or the yz plane, is going to be the triple integral over omega, which is a rectangular region, so just from 0 to 3, from 0 to 4, and from 0 to 3 of the density function, which is z e to the x plus y, and this will be times x dz dy dx. And after a number of different computational steps, similar to the integration before, you end up getting that this is exactly going to be 9/2 times -1 minus 2 e to the 3 plus e to the 4 plus 2 times e to the 7th, which is approximately equal to 9,930.12. And the units of a first moment are in what are called kilogram meters. Because the units of the volume element are in meters cubed, the units of the density function are in kilograms per meters cubed, and the units of this x here are just in meters. Say if you're dealing with SI units. So the units of a moment are in kilogram meters, or in general of mass times length. In a similar manner, we can compute mxz, or the y moment. So this will be the triple integral over our region of the density function multiplied by y and again I'm just going to skip the computations here. It's a good problem. All of these are good problems to practice your triple integration over rectangular regions, but this ends up being exactly 9/2 times -1 plus e to the 3 minus 3 e to the 4 plus 3 e to the 7 kilogram meters, which is approximately equal to 14,153.4. And then lastly, the z moment, or mxy, will be the triple integral over omega, so from 0 to 3, from 0 to 4, from 0 to 3, of the density function, z times e to the x plus y, times z. Which has an exact value of 9 times 1 minus e to the 3 minus e to the 4 plus e to the 7. Which is approximately equal to 9,206.55 kilogram meters. And so when we go through and plug all of these values in to our center of mass formula, which we can directly go through and do, because we have that the center of mass coordinates for each ordinate is just the relevant moment divided by the total mass of that region. We can go through and actually check on these and compute each one of these values. We have m and we have all of the moments. And when we do that, when we go through and plug in here, you take a yz moment and you divide it by the total mass, you get that this is approximately equal to 2.15718 meters. And you plug in for the y center of mass, you get the y center of mass is approximately 3.07463 meters. And you get the z center of mass actually is exactly 2. So all of these are much different than that centroid that we talked about earlier. The centroid, remember the region is 0 to 3 in X, 0 to 4 in Y, and 0 to 3 in Z. So if you go through and use those centroid formulas that we went over earlier, you'll get the centroid is exactly equal to 3 halves, or 1.5. It's the x coordinate of the centroid. The y coordinate of the centroid is going to be 2. And the z coordinate of the centroid is also going to be 3 halves, or 1.5. So you see very clearly that the center of mass is being shifted to the right along x, shifted to the right or in positive y direction, and shifted up along the z direction. So into the positive z direction, because the distribution of mass is more heavily weighted towards the upper corner of our object. You'll remember that from the picture that we showed earlier. So this is a very, very kind of cool example to kind of show exactly how to use these formulas in practice with a function. So I guess that the last thing that we want to do is we mentioned that we want to find the moments of inertia of this object, and this is another good example for finding the moment of inertia. Again, I'm not going to calculate the integrals, but I will show you how to set up the integrals and what they will end up being, so you can go through and compute them yourself. They're all rectangular integrals, and the problems are all going to be similar problems to the problems that we've gone over for rectangular domain triple integrals. So the moment of inertia about the x-axis is going to be the triple integral of the density function, which I'll just plug directly in. It will be z times e to the x plus y times y squared plus z squared dz dy dx, which will end up being exactly 9/4 times 13 minus 13e cubed minus 29 e to the 4th plus 29 e to the 7th. The units of a moment of inertia are in kilogram meters squared, and this will be approximately equal to 67,435. The y moment of inertia will be the triple integral of the density function times x squared plus z squared which will be equal to 9/4 times 19 e cubed minus 13 times e to the 4th minus 1, or 44,435 approximately. And the z moment of inertia will be the triple integral over omega of the density function times x squared plus y squared. which is exactly equal to 9/2 times 4 minus 7e cubed minus 12e to the 4th plus 15e to the 7th, which is approximately equal to 70,460. And remember that I chose not to go through and do these calculations out, but these are all good triple integral problems to help you practice going through and evaluating the triple integral on a rectangular domain. So I definitely recommend going through and doing that. And it's a rectangular domain, so we can also even just put the bounds in here for each one of these, so we have the exact bounds and we're integrating in Cartesian coordinates. So the idea here is that this tells us a good amount of information, though, with these values. We basically have that rotating this object about the z-axis, or around the z-axis, will provide the most resistance for us. So most resistance to rotation. With the x-axis not far off. The x-axis has a moment of inertia that's not, it's smaller than the z-axis, but it's not that much smaller. So the idea is that the rotation around the x-axis is slightly less resistance. And the least amount of resistance to rotation is the y-axis. That's the easiest axis to rotate this object around because it has the smallest moment of inertia, and it's much smaller than either ix or iz. So the least amount of resistance is, I'm going to say, rotational resistance is the y-axis. So this is it, though. This is how you go through and you use those formulas that we talked about. And this is a nice, long example, kind of showing how to apply each one of the formulas in turn and use it on a rectangular domain. So the last example that I want to consider today is a non-rectangular domain, because these are also important, very, very, very important to cover and understand how to go through and integrate in them. Specifically, we'll use an example where we have to use a different coordinate system to get our triple integral. And all of this stuff on coordinate systems will apply. So whenever you have to do a triple integral, you have a lot of different avenues for evaluating it at your disposal. But let's say we want to find the mass. I'm not going to go through and get the other. So I'm just going to go through and find the mass of the region. All of the other formulas still apply, and you can use the formulas to find the center of mass or the moment of inertia or any other really applied property you want to find of this region. But we'll just find the mass of the region bounded by the curves or the surfaces. Z equals 16 minus 2x squared minus 2y squared, and z is equal to 2x squared plus 2y squared. if the density function is given by rho of xyz is equal to the square root of x squared plus y squared. So this is saying that the density function it grows linearly as you move away from the z-axis. Now, hopefully you can see almost right off the bat what this region is going to be. It's going to be the intersection between a downward opening parabola and an upward opening parabola. So the space between a downward opening parabola and an upward opening parabola. Not parabola, but paraboloid. It's a three-dimensional surface. And we can open up my plotting program in Python just to kind of show this and see this. And so here we have a plot of this region in 3D. The region that's bounded by the paraboloid 16 minus x squared minus y squared above, and below by the paraboloid x squared plus y squared, with a mass density function of the square root of x squared plus y squared. So you see, if you kind of rotate this around, you see very clearly that in the middle of this object, so the center of this object, you have the lowest mass density in the object, and as you move closer and closer to the boundary of the object, or you get further and further away from the z-axis, the mass becomes more and more concentrated as you kind of move out towards the boundary of this region, the boundary of this object. So the idea here is we want to sort of take this and directly go through and calculate the mass of this region with a distributed mass density. And we can do this very, very nicely using those formulas that we talked about before. So the first step always is, these visualizations are very nice, but we want to see if we can kind of get an idea of the shape of this object without relying too much on the 3D graphics. So the idea here is that we can always go to the good old-fashioned traces, which we've been talking about for a while now, in terms of allowing us to figure out exactly what we're going to be integrating and what the domain omega in 3D is going to look like. So we'll consider the trace in the xy plane, the trace in the xz plane, and the trace of this object in the zy plane. And in the xy plane, the shape that we're interested in is the intersection of these two curves, because it turns out that when you go through and calculate the intersection of the two curves, you get that bounding circle. That it's kind of like the largest possible circle in the domain itself. And the idea is that this circle is going to be the circle that we're actually going to integrate over in when we go and calculate the triple integral. So this is given exactly by when z is equal to 16 minus 2x squared minus 2y squared, and when that is equal to the curve 2, or the surface 2x squared plus 2y squared, which gives us the equation 16 is equal to 4x squared plus y squared, or x squared plus y squared is equal to 4, which is a circle of radius 2. And I'll just use the circle tool here. to get a nice circle around the origin. So these two paraboloids intersect on this circle of radius 2. And this is going to be a very important region for us. We'll call this the domain D. And we'll call the circle as a radius of 2 here. So this is going to be a very important region for us, and we also then have the traces along each of the other axes. So the y trace, and say when y equals 0, you're going to see the function z equals 2x squared for a lower bound. And this point right here is -2 and +2. And you're going to see as an upper bound, I'll make it a little bit higher there. The function z is equal to 16 minus 2x squared. So y-intercept of 16. And this height right here is 8. So this is the trace of that region in along the zx plane, and you have the exact same shape actually along the zy plane. I have a upward opening parabola that's given by the equation z is equal to 2y squared, and you'll have a downward opening parabola that has the equation z equals 16 minus 2y squared, because this trace can be thought of as when x is equal to 0, just like this trace is when y equals 0. So there you have it. This is our non-rectangular region, the traces of that region. So you can do these traces without seeing the plot of the 3D function at all, and all of the traces give you a very good idea of the exact three-dimensional shape of our region. They're showing you directly that this region in 3D is going to look exactly the way the plot showed that it looks. We have up here at, say, z equals 8. We'll call this z equals 16. Then at z equals 8, you have a circle. A radius 2. We have a downward opening paraboloid. This is that top paraboloid. Paraboloid z is equal to 16 minus 2x squared minus 2y squared. And then you have a upward opening paraboloid below this. It's going to look like this, and then you have another trace, say, right here that looks like this, which exactly matches that three-dimensional plot that we showed earlier, but I didn't use any 3D plotting program to do this out, right? This is all done by hand, and it gives us an idea of the shape of our object. It also tells us what our correct domain of integration is going to be. Right, so this is, say, this region D that we're integrating over. Well, we're integrating over D, and D has a very nice upper bound and lower bound. At any point in D, the lower bound in Z is given by the lower paraboloid, and the upper bound in D is given by the upper paraboloid. Same thing right here. The lower bound in D is the lower paraboloid, and The upper bound in D is this upper paraboloid. And because D is a circle, I think that the easiest coordinate system to use for this triple integral is going to be cylindrical coordinates around this circle, this region D. So the relevant trace that we want to consider for this is going to be this trace. To calculate the total mass, we need to take the triple integral over the region omega of the density function and we're going to evaluate this in cylindrical coordinates. So you'll remember that in cylindrical coordinates, remember that the density function rho of x, y, z is equal to the square root of x squared plus y squared. And in cylindrical coordinates, x squared plus y squared is just equal to r squared. So the density function is just equal to r in cylindrical coordinates. So this density function is going to be r. And then dv in cylindrical coordinates is going to be r dz dr d theta, because r is the Jacobian determinant term when we move to cylindrical coordinates. And we can directly go through and compute our bounds as well. Theta is going around this circle D, so it's going from 0 to 2 pi. R, the radius in this region, is going from 0 to 2. And Z is the only real complicated bound. It's going from the bottom surface, which is the bottom paraboloid, or 2 times x squared plus 2 times y squared, which is 2 times r squared. And likewise, the top surface is going to be 16 minus 2 times r squared. So the triple integral that we have to evaluate is the integral from 0 to 2 pi, from 0 to 2, and then from 2r squared to 16 minus 2r squared of r squared, dz dr d theta. This is the integral from 0 to 2 pi of the integral from 0 to 2 of r squared, because r doesn't depend on z. The integral of 1 dz is just z. This is from 16 minus 2r squared to 2r squared. Which will be equal to the integral from 0 to 2 pi, integral from 0 to 2, and when you plug in the bounds for z, becomes 16 minus 2r squared minus 2r squared, just the fundamental theorem of calculus to that antiderivative. And this simplifies to the integral from 0 to 2 pi of the integral from 0 to 2. This will be r squared times 16 minus 4r squared dr d theta. And this integral is relatively straightforward to go through and evaluate. the integral from 0 to 2 pi. This will be the antiderivative of 16 times r squared, which will be 16r cubed over 3 minus 4 times the antiderivative of r to the fourth, which will be 4/5 r to the fifth from 2 to 0. So this ends up becoming, when you plug in and do the arithmetic on this, you end up getting exactly 256 over 15. Which then is just 256 over 15 times the integral of 1 d theta, which is just theta from 2 pi to 0. So your final answer for the mass is going to be 256 over 15 times 2 pi, or 512 over 15 times pi kilograms. And this is how you go through and get the mass, even if your region is non-rectangular. You set up the integral, you choose the bounds of integration and the coordinate system, right? You find the bounds of integration after you choose the correct coordinate system, and then you go through and evaluate the integral in that chosen coordinate system. Now, it's important to emphasize that all of the other physical properties can be calculated like this. So that's the center of mass, right, and the moment of inertia. As well as many other physical properties that can be calculated using the previous formulas. You just need to set up the integrals that you need to evaluate, choose your coordinate system, and then go through and evaluate the integrals. But thank you very much for tuning into the lecture today. That's going to conclude today's lecture, and I hope you had a great day.